This little video continues the story of hypothesis testing. We'll also talk about strengthening of testing, and we'll give you some example problems. First off, for strength of testing sorts of decisions, the tester controls the probability of a type 1 error, right? So you've got, here's your curve, and remember, this is actually, I'm going to erase this. Remember, overlying all of this is the real distribution, and then this is so it has a sigma, and this is the distribution of the sample means, right? So it's sigma divided by the square root, and that's the sample standard deviation. So this sample standard deviation will have an alpha, a type 1 error. There's our alpha. That is the probability that we will randomly get a sample. Boom, over here we get some x bar out of a bunch of we take a bunch of samples, we average out our x bar, and we find out that, whoa, it's way away from where we thought that the mean actually was. What's the probability that we are, in some sense, outside the region of the null hypothesis? So what do we really mean by null hypothesis? The null hypothesis means that, well, here's the mean, and we're assuming that in our sample that this assumption of the true mean being here is the same as what we're hypothesizing it to be. So in other words, there's no difference in between where we're supposing the mean is and where the true mean is. So that's why they call it the null hypothesis. There's no difference. And of course, alpha is the probability that our sample mean will fall outside of the area that we've designated as the null hypothesis. The rejection of the null hypothesis, the fact that we fall way outside where we think mean in this example actually is called a strong conclusion. And more than that, the probability of falsely rejecting our null hypothesis can be reduced by just appropriately selecting our AL and AH. So if we make this bigger, right? If we make, see, I've just had a one-sided alpha there, but if we make this, let's say that our acceptance region is right here. Well, I'm going to outline it in green. So that's our acceptance region right there. And if we change our alpha, if we make alpha be larger, then we increase the probability of falsely rejecting the null hypothesis. If we make alpha be smaller, move it out towards the edges here, right? So it's just this portion. Then we reduce the probability of falsely rejecting the null hypothesis. But the probability of a type 2 error, beta, depends on the true value of the parameter. So if we have a decision to accept the null hypothesis, that's called a weak conclusion, unless the value of beta is acceptably small. So in general, we use the term fail to reject the null hypothesis instead of accepting the null hypothesis as true. Now, I'm going to show you, give you a little bit of an example, but before we do that, we should cover one last term, and that is the power. Here we go. There's the power right here. It's just 1 minus beta, and that's the probability of rejecting the null hypothesis when the alternative hypothesis is true. So in other words, it's what we want to do. It's just our null hypothesis is wrong, and we realize it's probably wrong, that is. The power is a measure of the sensitivity of a hypothesis test. Now, the best way to look at this, I took a screenshot here so I can write on it. But if you look here, we've got a standard deviation, right? That's for actually, now remember, this is sample means right here. So this is actually sampled from some larger group, let's see here, I'm trying to kind of give an indication that this actually is the sample means taken from much broader distribution. This has a distribution of sigma, this has a distribution of sigma x bar is equal to sigma over the square root of n. So there's our sigma here, and actually in this particular case I'm gonna cheat and put that right in there because that's what this actually is sigma over the square root of n. And now what you see is, look, here's our null hypothesis that a mean, for example, falls right here. Now, default is the sample standard deviation is 1. So that means that however far we move this del, that's the mean of this, the distance of the mean of this other. So this right here, this distance right there is del, is this number right there. And n is the number of samples we take. Alpha, right here, is, in this case, it's going to be this value right here, which is actually 0.5. Okay, so we got this 0.05. That's that value. Now, what they're trying to say is this is the significance level. Alpha is the significance level. Let's write that down. Alpha is equal to significance level, and 1 minus alpha, which is all this stuff that I'm going to color in blue right here. That's 1 minus alpha is equal to the confidence level. And remember that alpha is the probability of a type 1 error. And then we have beta. Beta is the type 2 error. And in this case, let's see, what can I color it in with? Well, I guess I'm going to have to use, I'm going to erase. Ha, you didn't have to hang on very long there, did you? Okay, so what is beta? Beta is going to be this blue area right there. Here's our beta. And remember, this is the probability that we will falsely accept the null hypothesis. And then lastly, we've got 1 minus beta, which is the power, which is that we are correctly rejecting the null hypothesis. So let's see, I've defined this beta and 1 minus beta. Alpha is the type 1 error, and that is simply that we falsely reject the null hypothesis. And lastly, our confidence level is that we, this one right here, is we fail to reject the null hypothesis. So that says reject right there. Kind of went off the edge. Okay, so now you've got it all. I'm going to go to the actual simulation now because it's kind of cool. Okay, so let's take a look here. I'm going to do, let's see, an upper level, upper tailed, right? So if you look here, we can see that if I increase n, right, that has an effect, makes it tighter. Decrease it, makes it lower. Okay, so we'll mess with that. Now we'll look at, here's the power. And the power, remember, is that we are correctly rejecting the null hypothesis. In other words, our x bar probably fell in this region, and so it indicated that, you know, it's a good chance that the true mean falls more over here under the red area. So let's see. But what's this alpha? The alpha is, well, look, 0.05. That means the probability that we will falsely reject the null hypothesis is 0.05. We can make that, look at that, smaller. So when we decrease alpha, then we falsely at the same time, we increase beta, which is the probability that we will accept the null hypothesis when the alternative hypothesis is true. So you may want to pause this and think about these things. Remember though, if you are decreasing alpha, you are also decreasing the power, which is 1 minus beta. Let's look at how all these things interact. Watch. I'm going to, increase alpha, right? So that's the probability that we will falsely reject the null hypothesis. And as I increase alpha, right, the power actually gets better. And then at the same time, beta, that is the probability that we will fail to reject the null hypothesis when the alternative hypothesis is actually true, that gets smaller as we make alpha become bigger. And likewise, as alpha gets bigger, then the power becomes larger. And then we can mess around a little bit here. We can make things be a little bit further apart. And let's make our alpha be smaller again. Okay, here's our alpha. Now watch, the power we're reducing the power. Okay, that's where it's starting to get a little bit interesting. And that's about as small as we can get on our alpha. So anyway, you might want to pull this up and give it a try. It does have some different types that you can, here we go, there's our two-tailed distribution right here. So again, we can take our alpha. Okay, so now we've got our alpha. This is 0.11. That means the area under this and the area under this side. And we can, let's see, take this out a little bit, move them in or out. Now notice that when I move these sample means really close to one another, the power gets really low. And that's to be expected, because you can see if you get a sample anywhere between this range in yellow right here, then what happens is you will accept the null hypothesis, but in actuality the alternative hypothesis is the one that's really true. And you will only spot that the alternative is actually true for this small area in red. Actually, if I move it a little closer, you'll see the red actually shows up on both sides. So if the null hypothesis is pretty close, right, then we can't pick up on it very easily. I mean, if the alternative hypothesis is close to the null hypothesis, and we can figure that out by the power. So in the previous example with the welding strength, if n was 10, then the power would be 1 minus 0.2647, which is 0.7357. And that just means that we would, 73% of the time, would correctly reject the null hypothesis. So one method to conduct a hypothesis test, and this is a little bit lengthy, but it's actually all just common sense, so not to worry. First, you identify your parameter of interest. You state your null hypothesis and whatever the parameter is. Sometimes it might be one-sided or two-sided. Specify the appropriate alternative hypothesis, H1, for one-sided or two-sided, of course. Select a significance level of alpha. That's the probability of your type 1 error. Common values are 0.05 and 0.01. Determine your test statistic, right? So you're going to maybe take a bunch of samples and then you'll end up with your sample mean. And determine the acceptance region, right? That's going to depend on your alpha. So basically your alpha sets this acceptance region. Select your sample size. Conduct your random sample, right? Well, this is actually where you get your X bar, but that's the one that you've determined you wanted to get right there. And finally, draw your conclusion. So you can fail to reject your null hypothesis, otherwise you can reject the null hypothesis if it turns out to be in the critical region. So for an example, we can have an airbag that is required to inflate in an average of 32, well, I'm going to say microseconds because that's what we have down here, in 32 microseconds. The standard deviation is going to be, say, 2 microseconds. The experimenter sets a significance level at alpha is equal to 0.05, and then the experimenter randomly selects n is equal to 10 airbags, and they record the inflation times. There you go, there's your inflations. What conclusions should be drawn from the hypothesis test? Well, this is pretty straightforward. Our parameter of interest is the inflation time, the average one. Our null hypothesis is that the mean is 32 microseconds. And our alternative is that it's not equal to 32 microseconds. We've got our significance level of 0.05, and our test statistic is actually the z-score, right, which is considered to be an element of the normal curve, and we can calculate it in the usual way. And remember, this is sigma divided by the square root of n. And then we would determine the acceptance region. Well, gosh, if we're dealing with 0.05, then we would just go look on our usual tables. We know that if it's ranging between if it has an area of 0.95, we've calculated this earlier, basically the z-scores that will give us 0.025 here and 0.025 here are going to be minus 1.96 and plus 1.96. So the estimated value of the parameter is actually, we just add it all together and divide by n, and that gives us 33.6 microseconds. Converting that to a z-score, right, with our usual methodology, gives us a z-score of 2.53. The conclusion is, well, look at this, 2.53 is like way past. So it's like 1.96 is here, we're out here, right? So it's 2.53, and so that means we reject the null hypothesis at the 0.05 level of significance. And note that there's strong evidence that the mean inflation time exceeds that 32 microseconds, right? Because the probability, if this truly was at 32 microseconds, the mean, then the probability that we would be that far away is pretty small. So a way we can quantify things even further is by using the idea of a p-value. And that is the smallest significance level that will result in rejection of the null hypothesis using the given data. So we recall that the significance level is our alpha. If the test statistic is thought to be a z-score, that's a member of the usual normal curve, and the null hypothesis is that our mean is going to be at some mean, pre-specified mean, then we can say that the probability, or rather the p-value, is given by these different values. First, we can say if it's one-sided and we're looking for the probability that our mean is going to be less than some, mu naught, so we're looking that it's going to be down here somewhere, wherever, below it, then it's going to be the probability of this f0. So let's say that we get a z naught, we calculate it all out, and it turns out to be whatever that z naught is. Then this area right here is the p-value. Now let's say that we instead have one-sided upper tailed. Okay, well then it's just going to be well, we'll use a different color here. So it'll be something like if our z0 falls right here, well, that's going to be the probability that's greater than that z0, and so it's going to be clearly 1 minus is the value, because that's actually 1 minus this value will give us this blue value right here, solid blue value. And then if it's two-sided, then it's essentially like we got to take this value and then which is 1 minus fc at z0, and then we're going to take that value and we're going to double it, and that's the p-value for two-sided. Now, for a p-value method for conducting a hypothesis test is really similar to what we've just done, and so we just first specify the parameter of interest, state our null hypothesis, specify the alternative, one-sided or two-sided, determine whatever our test statistic is, and then select our sample size and conduct the sample, compute the estimated value for our test statistic, so there's our x bar, compute the p-value using the estimated value of the test statistic. So you get here, and let's say here's your mean that you're proposing, and then you find something that's way over here, and then you can say that this area right here, this area would be the p-value for a one-sided alternative hypothesis. And then you draw your conclusion that H0 will be rejected at any level of significance, right? That alpha is greater than this particular p-value. And then you just want to know, is that p-value actually going to be okay? So for example, if we say that our p-value here, let's say that this p-value turns out to be 0.01, and that means that our null hypothesis will be rejected if any value falls outside of, or if any x bar falls outside of this range. Is 0.01 good enough for you? For my purposes, I would think it would be very good. But let's say our p-value turned out to be 0.05. Maybe that's not so hot. What if our p-value turned out to be 0.10? That means 10% of the time you're going to reject your null hypothesis, but you shouldn't have. So this gives us an idea of all of that. Now, let's do an example. So we can repeat the previous airbag hypothesis test using the p-value method. Steps 1 through 5 are the same. Step 6, if you take a look for that z value, you find that p is equal to 0.0114. Now, where did I get this 0.0114? I'm going to go back a couple slides, and we'll see. Now, here's 2.53, right? That's what we found right here for this z statistic. Now, we go look at 2.53. Okay, so we're back to our usual. We've got 2.53 here. So it's 0.994297. So here I've got it outlined for us. And let's take that. I'm going to move it over a little bit. If we go 1 minus 0.99, well, you know that's a 0.994297. This just won't let me write very well. Well, this will let me write better. So I'll say this value is actually equal to this 1 minus 0.994297. So that's where this value, this p-value, came from. So the hypothesis, the null hypothesis that the mean is 32 microseconds will be rejected for any level of significance alpha is greater than 0.0114. And recall that the null hypothesis was rejected in the previous example at alpha is equal to 0.05. But what if we don't know the standard deviation? If we don't, then we can do a good approximation by just saying our sample standard deviation is approximately equal to the standard deviation. If n is greater than about 40, well, that'll work pretty well. If n is smaller, we want to use the t-distribution for the test statistic. So now let's have an example, and this one says a particular car, they claim that they've got an average of 28 miles per gallon. Okay, so a random sample of 12 cars are tested and we get the following fuel consumption. Does this data suggest the car averages more than 28 miles per gallon at the 0.05 level of significance? Well, what have we got? We've got a parameter of interest of mu is equal to the average miles per gallon. And our null hypothesis is that H naught is that the mean is 28 miles per gallon. The alternative hypothesis, H1, is that the mean is actually greater than 28 miles per gallon. And we're going to have a significance level. They already tell us up here, 0.05. Alpha is equal to 0.05. Now our t, well, we're going to use a test statistic, and it, since we've only got 12 cars are tested, so we're going to use a t-statistic, right, because there's only 12, and then we're going to have k is equal to n minus 1, which is 11 degrees of freedom, and t is going to be equal to x bar minus mu, or s, divided by the square root of n. And what is our s going to be? Well, in this particular case, we'll calculate it using our usual formula, which is x1 minus x bar squared, and then plus, well, a bunch of other stuff, and then we'll go xn minus x bar squared all over n minus 1, and this all equals 1.2 when you work it out. Okay, so now take a look at all of this. Make sure you've got your notes, and then I'm going to erase everything magically. Probability that we're going to reject the null hypothesis when the null hypothesis is true is actually alpha. And that probability is AH, that our t is actually going to fall above AH. And that's got to be 0.05. So use the t-table. Alpha is equal to 0.05. K is 11 degrees of freedom. And let's bring that up here. So here we go. Okay, we got it right there. So 0.05 is right here, and 11 degrees of freedom. So we can see, well, if you take a look on this, so 11 degrees of freedom, 0.05, and we're going to be at 1.796. Hopefully my pointer shows that. 1.796. So t at alpha is 0.05, and 11 degrees of freedom is 1.796. So now we figure out our x bar. And we do that by adding I is equal to 1 to 12 of all our xi's, and divide all that by 12, and we turn out we've got 28.8 miles per gallon. Ooh, that's looking bigger than 28, right? So now when we take that x bar and we use it to calculate our t-score, our t-statistic, we have x bar minus mu over S divided by the square root of n, and that's going to be 28.8 minus 28 all over 1.2 divided by the square root of 12, and that means that t is equal to 2.31. Ooh, that sounds like that's going to be way out there, right around here. So our conclusion is that since this t, well, I'm going to write this in black here, t is equal to 2.31, which is greater than 1.796, which is our upper limit. We then reject the null hypothesis at the 0.05 level of significance. And there's strong evidence then that the average fuel mileage exceeds 28 miles per gallon. Check.